Welcome back to our lecture series on AutoML. We are still in the age of foundation models. Now we would like to talk about LLMs for automated discovery, which is one way to see how one can leverage LLMs and goes a bit deeper than previous videos. The challenge is traditional optimization algorithm design rely heavily on human intuition and manual iteration, which limits scalability and adaptation to complex and novel problems. Especially really this kind of scalability is an issue. What can humans actually really try? How patient they are in doing things? How many humans are actually available to do it for a new problem? And the opportunity with large language models is they have demonstrated remarkable capabilities in code generation and pattern recognition. By combining LLMs with evolutionary algorithms, we can automate the discovery of novel algorithms and mathematical constructions. So the core concept behind all of that is that we're using now LLMs as more as an intelligent mutation and crossover operator within an evolutionary framework. So instead of randomly mutating code, the LLM uses its prior knowledge from all its training data and so on to propose hopefully plausible high-quality improvements and searching thereby effectively through the vast space of possible programs. You can imagine that if I have a code program and I'm shading one line by something random, by some kind of random operator, most likely that will not lead to a very good new program. My large language model have the chance actually produce a variation which is still plausible. We can still run and hopefully even achieve higher quality or higher performance. We started to go through some of these ideas, and maybe one of the earliest one in that direction was fun search, searching in the function space. The idea of fun search is that it pairs a pre-trained large language model with an automated evaluator to discover new mathematically constructions algorithm. It maintains thereby a pool of high-scoring programs and iteratively prompts the large language model to generate improved versions. So we're starting more or less with a program database, which can of course be empty at the beginning, or we can put already all kinds of valid programs into that. Hopefully also diverse. I will not start with this with a single one. And more all kinds of solutions we know from humans maybe, which solve the same problem. The nice thing, of course, you can use large language model already to populate this kind of program database. More as a deep research task, find me all kinds of programs which are solving that kind of problem from literature. And then what we're doing is best shot prompting. So the LLM is prompted with a skeleton of the target function. So that skeleton should somehow regularize what it should do and prevent that it goes completely amok. But it's more or less, there's a structure we're expecting. Right, so could be, for example, if you think in terms of Bayesian optimization, there has to be an acquisition function, there has to be code for optimizing the acquisition function, there has to be code for the surrogate model, right? So there are certain parts, that's the skeleton, where we say, okay, that needs to be there, and only now needs to fill these kind of components. And of course, we also feeding in top performing implementation from the database and say, okay, that should be the inspiration models for the LLM it should make use of. And then it's doing automated evaluation, so generate programs and are scored based on a systematic evaluator, which needs also be given and decided by a human user, right? So you need to decide, okay, how to do evaluation, but it should be more or less, the LLM should be able to run that evaluation automatically without your further input. And then very common in evolutionary strategies, incorrect or low-scoring programs are discarded, may not put into the program database, and the very performing one should go in there. Then there was also a paper which is called the Darwin-Gödel machine, which is then on open-ended self-improvement, and the algorithmic ideas goes more a step further and saying, inspired by the theoretical Gödel machine, the Darwin-Gödel machine, DGM, continuously evolves an ancient self-improvement logic. It focuses on open-ended evolution, where the AI autonomously modifies its own code to adapt and perform better. doesn't sound too much different than before. Let's see some details to it, which makes it a bit better actually. The system leverages LLM to propose modification, not just to its solutions, but to its own evolutionary and learning algorithm in addition. That makes it very cool that we can also say, okay, how we should also reflect on ourselves, how to improve further. It's also doing an open-ended exploration, so it shifts from optimizing a static objective to endlessly discovering novel behaviors and capabilities. You can more see that as a tree. So you're starting with a solution or a bunch of solutions, and it then creates offspring of that, so modified more or less code or algorithms, and then has to also decide what to go next, what is the most promising direction, then maybe going here again, and so on, right? So if you have seen tree-based search, it's a bit similar, but it has to decide on its own where to go next and what is actually interesting. So was doing some kind of meta-learning automation. So meta-learning in a sense, we doing it over and over again, solving problems and trying to figure out what works well and what not. It automates the discovery of the optimization algorithms themselves and building upon previous artifacts cumulatively. Here a bit visual that maybe it's better to understand what's going on. So we have this kind of tree I showed you before. So each of these nodes here is one program. You can say we have these kind of parents, gets into a coding agent, which is then some kind of self-modification. So we have the coding agent's own repo. We have self-improve instructions. So it can reflect on how it should improve. And that's fed into the coding agent. That gives us now a code diff, more a modification of our previous parent. Then this is again fed into to a way that we can generate now a new coding agent, right? So we would like also to learn from that what we need to change also for the future. So it's more also doing an evaluation on itself in that second step. We're doing the evaluation on benchmark and add that child to our tree. And now the LLM can pick from the tree again where it believes is the most promising part, can do more generating an offspring, new more modification of our tree, and also trying to update on its own how it should do modification. Furthermore, there is Shinka Evolve. A very recent paper was now accepted at iClear 2026. And the algorithmic idea behind Shinka Evolve is that it addresses the sample inefficiency of previous code evolution methods by introducing new sampling and selection mechanism to balance exploration and exploitation. So that's, you're seeing why that is already very close to what we always talk about in automated machine learning. It's always about exploring and exploiting, right? And the main point here is actually to decide what is novel. So not only to say that we would like to go for the most promising in terms of performance, but also trying to do something which should go to novel solutions, right? Because if you're only doing small updates, going to local optima, it might not be very efficient. So we would like to strive for novel ideas. And therefore, we have this novelty rejection sampling as part of Shinka Evolve. So it prevents the LLM from redundantly exploring the same search space by rejecting semantically identical or overly similar candidate effects. So you can imagine that if we have these kind of trees where it's doing something, and maybe it's generating here something, but it sees, oh, that is very similar to what I had seen before. So then we don't spend the time in doing evaluation here, but more directly rejecting that and saving, of course, with that, again, tremendous amount of times and focusing more on really novel parts. The end is a Bennett-based LLM ensemble, which is used for that, for this kind of novelty scheme. So dynamically allocates generation budget among a diverse ensemble of LLMs using a multi-armed Bennett strategy to maximize the quality of these mutated programs and saying that we're not only doing one LLM, but using many of them, and we would like to decide which LLM is the most promising one to get us new, better, also novel ideas, and we don't stay with the same LLM all the time, but more combining the strengths of multiple of them, and therefore, as I said, maximizing the quality overall. To also visualize that slightly here, so we have a code, right? We're doing some large language model embedding. Can now also compute similarities to previous solutions, doing some thresholding on that. So what was the most similar ones, and figuring out, okay, how similar is that overall? So what was the most similar things we have seen before? And then we can decide here again, even LLM is used, it's not a threshold directly. So, or to put it differently, if there's exceeds a threshold, the maximum one, in that part here, then in addition, a large language model is used to judge whether the code is novel enough or not. And then we're doing resampling a new program based on that. So that's this kind of novelty idea we have here. Then another idea is LaMEA. So LaMEA stands for LLM Evolutionary Algorithm, and specifically targets the automated generation of meta-heuristic optimization algorithms, for example, EAs or BO. And iterative designs, evaluates, and refines optimization algorithms tailored for given optimization tasks. So it's important to really see that we follow this idea of LLM as a designer we talked about before, in the sense that now trying to generate something which is then used to solve the actually underlying problem. So the LLM receives a prompt outlining the algorithm structure, for example, again, initialization steps, selection, and so on, which we called, for example, something like a skeleton before. And then iteratively refines that, it generates new meta-heuristic, evaluates them on the benchmarks, which like BB or B, so it's a black box optimization benchmark, and feeds the performance back as a prompt to the LLM. Very important to note is that hyperparameter optimization on that meta level, so how to run, for example, the Bayesian optimizer, can be taken care either by the LLM or by an external tool such as SMAC or QNA. But from all the evidence I've seen so far as of beginning 2026, external tools, so specialized algorithms taking care of them is so far better than directly asking the LLM. Of course, one could now imagine that we using that kind of LaMEA approach to find an optimizer, which is then optimizing all the hyperparameters generated by the code for LaMEA. So one could again stack more or less ideas here on top of each other. So the synthesis is we have an LLM evolutionary paradigm on that. There's a common thread among all of these methods. The fundamental paradigm treats code generation as an evolutionary search problem, with the LLM serving as the source of variation. The core components, so we have some kind of representation. So the solutions are typically code functions or classes or part of a skeleton, but it's code overall. The LLM is then used for the variation of that code. It's doing some kind of mutation crossover, heuristic guided by prompts, of course. And then we're doing some kind of evaluation which often needs to be defined. We can, of course, combine that with some kind of novelty constraints, but overall, we have a sandbox execution against benchmarks, mathematical evaluators, or simulated environments, where we can then automatically, efficiently check how well something is going. And then the last part is some kind of a selection. What kind of solutions should be archived? Or what kind of strategy should be maintained to have a high fitness and diverse code base, which then helps us to have new, better variations in the next step. As a summary, we have seen now code generative models as an optimizer, so on that kind of meta level models, so pre-trained models can transcend their training data by acting as an intelligent search operator in a larger iterative framework. We need a verifiable output. So why the LLM might hallucinate? The nice thing is we doing the real evaluation still, so we don't use here LLM as a predictor, but really say, okay, there is some kind of real evaluation going on. Therefore, we can be sure that we're getting verifiable, high quality discoveries overall. This also goes hand in hand with this idea of continuous self-improvement, which is quite an old idea. For example, Jürgen Schmidhuber talked about that already, I don't know, 20, 30 years ago. And it's the trajectory of modern AI system, which is shifting from a static human designed architectures towards open-ended self-modifying systems. Efficiencies through meta strategies. So as the search space of algorithms is vast, incorporating diversity preservation is quite important. We have seen, so saying, okay, we would like to have diverse things in our program database. We have seen it's these kind of novelty search. We like to prefer actually novel options and going more in that direction. And even meta learning to significantly boost the sample efficiency and the rate of discovery. So it's not saying, okay, we can only prompt the LLM and everything goes well. We need further ideas on top of that actually to ensure that these kind of systems are efficient and really doing a good job. With that, we are at the end of the session. I hope you have some new insights and really state-of-the-art new ideas on how to leverage large language models to generate new code, which of course can be optimizers for AutoML or could be directly also model code or architectures even. With that, I hope we see us again in the upcoming videos.